Hi everyone. Uh, Can you hear me?
Yes, you're audible.
Yeah, okay, great. I'm Lalit and we'll be discussing things based on week 4 lectures for the course Computer Vision and Image Processing. Okay, with that, let me share my screen. Okay, I hope my screen is visible. Uh, let's start the discussion. So, what was done in week 4 lectures? Anyone? What were the topics covered in week 4?
Image transformation based on DFT, DCT,
Yeah,
and
orthogonal basis
orthogonal. Yeah.
and yeah, orthogonal basis, and these are sinusoidal basis specifically, and we
Yes.
have non-sinusoidal as well, I guess. Yeah, that was also been done. Apart from that,
Based on statistics
statistics, yeah,
input.
and then
The one was
another one is
Fourier
directional.
transform.
Sorry,
half transform. Uh,
half transform has not been done, but yeah, that's a part of directional transform. So
Directional transformation.
yes, that was covered, at least one of the transforms, which is the radon transform, has been covered in week 3.
Yeah. Yeah.
Yeah. So, okay, so what do you, so let's go through the lectures very briefly and then we'll start with the questions. So we started with DFT. What is DFT? At least the full form.
Discrete Fourier transform.
Okay, what does it do?
It gives the image interpretation in frequency component, frequency domain.
Okay, what is frequency?
Rate of change of grayscale value in the image.
Yeah, I
Yeah.
mean rate of change of the signal. So, I mean in image, your signal is the grayscale value or color values. It's not specific grayscale, but yeah. So we are just trying to measure the rate of change. Wherever there is a rate of change, there we call as frequency. For instance, what frequency is your fan moving? So it's like how many times the revolution has occurred. So we are just trying to measure the rate of change of some quantity. So that is frequency. Now, based on how do you measure frequency? It's the linear frequency that we generally see, or the angular frequency, which I gave you an example of the fan. And so we'll be considered with the linear frequencies or just the frequency as such, uh, what they call in literature. Mm, okay. So, okay, you are trying to interpret frequencies. What is the frequency component of the image or rather a signal using DFT? What kind of signal do you need to use DFT?
Discrete signal.
Yeah, it's a discrete signal. And what is the output? Output of a DFT?
Discrete.
Yeah, output is also discrete. So there are also a bunch of numbers in the frequency domain, as someone pointed out. So yeah, so what are the two main components of that frequency domain? Uh, so what kind of numbers are these DFT transformed signals? I mean, what does DFT give you? Is it real always, or it can be complex?
Real and imaginary, complex,
Yeah, so
imaginary.
in
Yeah.
general, it's a complex number.
Yeah.
So for complex numbers, you can get something called as magnitude and phase, which is same as what we defined for complex numbers. The magnitude is what? Magnitude is just the square root of real part squared plus imaginary part squared. And the angular part is, phase part is theta, which is tan inverse of imaginary part upon real part. Okay. So given this, what class of transform does it fall into? DFT.
Sinusoidal transforms.
Yeah, it's a sinusoidal transform, but more importantly, it's a unitary transform or orthogonal. I mean, for this specific case, we should use unitary because it includes complex numbers. So it's a unitary transform, and the bases are sinusoidal. Okay, and there are a few more properties. I mean, yeah, we'll go through them as we discuss the questions, specific questions. What else did we do? What is DCT?
It's a discrete cosine transform.
Hmm. So what do you do there? Why DCT? And what are you trying to do with DCT in first place? What does DCT give you? It's also some frequency domain interpretation, right? You have frequency parts. If I remember correctly, they used K1 and K2 as the frequency variables in the class. So it's also a frequency interpretation, but there are a few things that needs to be noted down. We'll do that as well during the uh, as we solve the questions. Okay, next, what did we do? Apart from sinusoidal basis, what else did we take as basis? Someone said it's just at the start of the session. What was that?
Non-sinusoidal
Non-sinusoidal meaning? That's okay.
or
Uh, Anything specific? What kind of
Hard,
transform?
hard transform,
Wavelets. Yeah, our transform.
wavelets. Yeah,
Yeah,
wavelet
it's
transform.
part of wavelets. So what was done in wavelets? So yeah, we'll go there. But before that, any other transform that was done?
And one
Short
more was
time Fourier
scale
transform.
transform.
Yeah, Carrion Lowe transform, if I spell out correctly. Yeah. So that transform depends on the statistics. What statistics are they dependent on? And statistics of what?
Of the input signal.
Yeah, of the input data. Yes. So here everything we are considering is a discrete signal. And what kind of statistics are you checking there? Now, what kind of statistics is this specific transform dependent on?
The covariance matrix.
And
Mean.
mean covariance. Yeah,
Mean.
that's correct. The mean and covariance. So, just a side question, nothing specific to KL transform. What kind of distribution can you specify using just mean and covariance?
Gaussian.
Yes. So if you have done a few probability courses, then they will always say that if you have mean and covariances, then there is an ultimate assumption that you are living in a Gaussian world. So yeah, okay. We'll go through the specifics of KL transform soon as we go through the question. Next, what was done is PCA. What is PCA?
Principal component analysis.
Okay. What is the main aim there?
Dimensionality reduction.
Yes, we want to reduce the dimension of the data given to us because In practical scenarios, we always see that the dimension of the input data is much less than where it is lying. Now, if you ask me what specific example should I give you, um, okay, yeah. So if I give you a set of points on a line, but it lies in 3D space, because when you measure, rather when you track a line in real world, it's 3D space, right? So you'll get all three coordinates. But the line is what? In which dimension does the line lie? Straight line. It lies in one dimension, right? Everyone agree?
Yes.
Yeah. So there is
Yes.
one dimensional data out there. Well, inherently it is one dimensional, but since you're measuring in this 3D space, so your data tends to have three coordinates. So three coordinates doesn't mean that the dimensionality of the data is three. It's just that your measuring space is in three dimensions. Uh, so what can you do now? You can do dimensionality reduction, assuming you have noise within tolerance level, and then you can make sure that whatever line you get is close enough to the actual line. Okay, so that's it with this PCA, and then someone said, yeah, wavelets. So why do we need wavelets?
To bring in the time component as well,
Why do we
how
need
the
time
Fourier
component?
transform changes with time,
Why do we need that?
because real signals are time varying and we need to see the
And
variation.
anything else? I mean, that's good, but any other motivation? So you have other transforms there, right? Fourier transform or sine transform. Why aren't you satisfied with that? So for when you apply these, yeah, someone was saying, yeah, yes. Okay, so when you apply these Fourier transform or cosine transform, sine transform, things like these, you see that when you map it to frequency domain from time domain, you lose information about which time what has occurred. So what it gives is, what these transforms, Fourier transform gives you is an aggregated information of what the frequency component is. And as someone said that yes, if the signal varies with time is fine, but the point is the signal is not non-stationary in the sense that some parts of the signal have some frequency components while other parts of the signal have other frequency components, then we don't know which part contains what frequency components. So to analyze it, first they came up with short time Fourier transform, but short time Fourier transform has this problem. And I mean, it doesn't have this problem, but you have to fix the resolution of the time, rather the window over which you want to measure the frequency. And because of this window, it's the great uncertainty theorem says that you cannot measure both frequency and time accurately at the same, I mean, given us same resolution. So that's why we come up with wavelets where we try to prioritize both frequency and time based on what is required more in the specific context. And then given that we come up with something called as wavelets. So these wavelets don't, so each specific basis wavelet, or it was called as mother wavelet in the class, each of them has varying frequencies, but they just live for some specific duration. After that, they die out. Die out means the other values are zero. And if you integrate over those wavelets again, the integration should be zero. That's the three properties the wavelet should have. And given that, I guess the last topic was covered is multi-resolution analysis. And why was it done is because you have different sizes of objects, or you have different frequencies to be specific. You have different frequencies in the images, and you want to analyze them based on what frequency component you want to uh, get attention of. Okay. Given this, I think we can start with the questions. Uh, Given this, yeah. So which of the following are the properties of 2D Fourier transform? So what is the formula for 2D Fourier transform? Or maybe just give me the 1D Fourier transform first. Anyone? Fourier transform here means I'm specifically speaking of DFT. What is the formula for DFT? The forward formula? Hmm? Is it that hard? Okay. Can anyone say what n is? Small n?
Input domain.
Yeah, time
Time.
domain or input domain, but it is discrete. Well, everything is discrete in DFT. What about K is the frequency domain,
Yes.
which is also discrete. What about N, capital N, is the number of uh, samples for which, or rather, I can just write it in other way. Time for which the signal exists. I mean, beyond N, you assume that it's zero. So your signal exists only for the small N, sorry, this capital N amount of time. So your signal, this is the signal part, and this is the transform, the one-dimensional DFT. Okay. So given this one-dimensional DFT, now can anyone extend it to write two-dimensional DFT? I will just change the uh, frequency variable notation so that we have more characters to use. M equals to 0 to n minus 1, 0 to what is this? X should vary with small m and small n. E power minus j twice by um plus vn upon n. So does everyone agree with this? I hope the variables are clear.
Yes.
M and n are the time domain or space domain variables. U and v are the frequency domain variables. Is this fine?
Yes.
Okay, so then given this, okay, which of the following is or are the property of the 2D Fourier transform? Separability. What do you mean by separability? So what is the kernel? Well, two-dimensional DFT kernel is what? 1 by n e to the power minus j twice pi by n um plus vn. How can you rewrite this? What do you mean by separability first?
It can be written as a. It can be separated for the two variables.
Yeah,
It can be
so
written as
two
a
variables.
product
I
of.
mean, yes, yes. You can write it as multiplication, the same function of the two independent variables instead of this joint one. So I'm writing something. If anyone has any objection in this specific thing, just let me know. I hope this can be written right.
Yes.
Yes. So since this property holds, that means it is separable. Agreed? So
Yes.
separability is fine. What about asymmetry? What is symmetry property? So let me call this as some function g of u comma m, and this is h of v comma n. So if you clearly see this, v and n are the variables used, and u and m are the variables used of the time and frequency domain. So is g comma m equal to h comma n? Or rather, okay, I should not write it this way. Mathematically, this is wrong. So I'll write it. If g of a comma b is same as h of a comma b, yes, right?
Yes. Right.
Yeah, so both are same. So they are symmetric. So this is the symmetry condition. So that means our asymmetry property doesn't hold true. What about periodicity? Is it periodic? Now, since you clearly see that they are separable and symmetric, if I prove something for one dimension, it holds for two dimension, right? Yes. So
Yes.
what if I write x of k plus n? So if I write x of k plus n, it should be what? Given the equation that we have above, is x of n e to the power minus j twice by k plus n upon capital N into small n. Everyone fine with this formula?
Yes. Yes.
Yeah, so minus j twice by k n by n into e to the power minus j twice by n. What is this value?
One. Right.
Yeah, how did you say that?
You can expand it into cos 2 pi
Yeah,
n
so
plus
this is what? Cos 2 pi n plus j plus or minus? It will be minus, right? Because we have minus there. Yeah, j sine 2 pi n. What is cos 2 pi n? It's always 1.
1.
So it's still a complex number, but we get a real number since it's 2 pi n out there. Okay, given this, what do we see? This is same as xk, right? Is it periodic?
Yeah. Yes.
Periodic with periodicity?
And
Periodicity and in what domain? In frequency domain. Okay, given that this is there, the periodicity part is fine. Non-conjugate property. What is non-conjugation? So let's try conjugating this. Conjugate means complex conjugate here. So what is our specific equation? 1 by root n summation of n equals to 0 to n minus 1. x and e to power minus j twice by k n upon n. Okay, and we have to take a conjugate of this. The conjugate of the whole is conjugate of the individuals, right? Is this fine? Is this step fine with everyone?
Yes.
Yeah. So we just took conjugation inside the summation and then each individual terms are just conjugated. That's all we did. So star means conjugation, and in complex number conjugation means if you change the sign of the imaginary term. That's it. Or rather, change the sign corresponding to j. That's all we do. Given this, what is it? Is this same as xk by any chance?
No.
Yeah, it's not same as xk. Why? Because we don't know whether this signal conjugation of this signal is same or not, right? And this is anyways not the same. So given that we know this, just one more property. If xn is real, what can we say about this specific thing?
It's equal to x of minus k.
Yeah, then x star is equals to x of minus k. Everyone agrees with this? Because then x star of n, small n is x of n, and this is what? This is minus of minus. You can write the other term as e power minus j twice by minus of k n upon n. So this leads to this thing. Everyone agrees with this?
Yep.
So I think everyone includes other people as well, not just that specific person. Any doubts? So non-conjugation property is false, and of course, all of the above is false. The answer is separability for this question. Any doubts with this question? So we actually checked a few small properties of DFT using this question.
What is the non-conjugate property exactly?
It depends how people say. I mean, at least what I know is conjugation will be the same as that of the original transform.
Okay.
So, I mean, this x star k should be equal to x. Okay, so we'll move on to the next question. Okay, so this question will at least, I mean, I'll try to check how much concepts were gained for the specific topic. Okay, find the KL transform of the matrix for this given image patch. That we'll find out. But what is KL transform? Mathematically speaking.
The kernel depends on the input data, statistics of input data, but for other transforms it is fixed.
Okay, that's fine. What is the specific transform for? I mean, can you write it mathematically? What does the transform look like for the KL transformation?
It's A into x minus mu x, where A is
Okay, A into
eigen
x minus mu x. This is some y.
y is equal to.
Okay, where?
X is the input image, and
No, x is input, like
yeah,
the
x
input
is
signal.
input. Yeah,
Y is
input.
output signal. It can be image or whatever.
And mu x is mean.
Mu x is the mean of what? Mean of input data
Input.
point.
Sorry. Yeah.
Input points, and A is what?
A is eigenvector matrix.
How do you define that? So A will be what? Like will be like E1 transpose up to En transpose,
Yes,
where again E1 to En are the I, eigenvectors of what? Eigenvectors of?
eigenvectors of the covariance matrix.
Yeah, covariance of X, which is the covariance matrix. Yeah.
Yeah,
Okay. So I mean, this is simply put what KL transform means, but why are we doing this? Anyone? Why do you need KL transform? What is the core idea? Why do we need this? Not just another transform.
Dimensionality reduction. That is.
You use the similar thing. You use covariance matrix in PCA to reduce dimensionality, which is fine. Anything more?
To find the most important component.
Both. Okay. Okay. That's fine. Most important direction, you can say, which is
it's
that.
mainly used for image compression.
No, it's used many places. Well, I'm not asking about applications. Yeah, you can actually compress data to some extent, but well, let's keep that aside. What's the main goal mathematically speaking? So why do we do this transform? Does this help us in any way? There should be some specific usefulness, right? Okay, fine. We'll go through it one by one so that you will remember it whenever you see this. So we have, mm, okay, we use this specific transform, but how is it coming? Um, so as someone said, we'll try to take these eigenvectors and then stack them into this matrix to get this transform. So what is the covariance of y given that you have this transformation? Okay, before we actually go into math, maybe let's build upon some intuition so that mathematics looks simple. I'll give you the same example now that I gave you a few minutes back, that I have 2D space where this is x axis, this is y axis, and then this is my specific line from which the data points are sampled. Okay, so the setup is clear, right? So given this line, we'll sample some specific points on this line, and then you would like to do what? The KL transformation. Okay, so what does this mean geometrically? So first, what are we doing? We'll take the main vector and remove it. What does it do here in the specific diagram? Can anyone say that? Given
Shift the
any line
origin.
like, yeah, yes,
Shift the origin.
it will shift to origin. Is it clear to everyone? Yes? No?
Could you please repeat?
So what are the steps that we do for KL transform? We first remove the mean, right? So what will it do to this line? Rather the set of points which are sampled along the line. Where will the points shift when you remove the mean of the points? Okay, so maybe we'll just do it mathematically so that it's fine. So if I let me call x tilde as rather xi tilde as xi is the given set of points minus mean. Well, mean is what? 1 by n summation over I xi, right? So given this, what is the mean of this? Summation over I x tilde I. What is this value? Can anyone tell me? Hmm? Anyone?
Zero, right? Then you mean will be zero
Yeah, how?
if you solve for
So can you tell me the
function
steps?
of xi.
This is right, right? The specific part is right.
Yeah.
Okay. And then is
And
something
n
like,
will cancel.
yeah, yeah. Tell me.
N and n will cancel for x
Yeah.
bar. So
And n by n into x bar. So which is what? This minus x bar, which is the same, right? That's how we defined x bar. Everyone agrees with that? Yes? No? So what will be the new mean? The new mean should be 0. How can it be possible that the set of these points shifted to some other place such that the mean is 0? What how will this point shift? Your new points will be here, right? Everyone agrees with that. All these points will be shifted like this. Everyone agrees? Yes? No?
Yes.
Okay. Pure silence. So what is it that you want to do? If you just take 2 points here, maybe just take these 2 points. Let us consider these 2 points as will be what? X is 0, y is 1, for instance, and this is x is 1, y is 0. So what is the mean of these 2 points? Half comma half, right? You want to shift the line or the set of points in such a way that the center, the mean is zero, right? So they'll shift in this specific fashion so that when you take the average of these 2 points, the average of these 2 points will lie along this line, right? The average will turn out to be here. I'm not saying this is shifting parallelly. It can shift like this as well. No problem with shifting like this. But whatever the line is, the line will now pass to the origin. Okay. Given that the line will now pass to the origin, your shifted points, these are the shifted points. The shifted points will look like this. Now, given this, I mean, the points are shifted because we set the mean to zero. Okay. This is what it does to a set of points on a line. Now, given this, what is there? We'll check the covariance, and it was mentioned in the class that make it it will just rotate your data, right? So what are the principal components in this specific, or rather the maximum the vector corresponding, eigenvector corresponding to maximum eigenvalue for this line? Anyone? So the eigenvector will lie like this, right? This or exactly the opposite direction, 180-degree opposite to this. Any one of them is right. So given that we have your eigenvector like this specific matrix is what? This matrix is what? It is a rotation matrix. Can you tell me why? It was discussed in the lecture. So can you tell me the formula for covariance? Everyone agrees with this formula? Yes? No? Covariance formula. Simple, right?
Yes.
Yeah. So given this formula, so covariance will be a matrix, right? These are vectors and these are the outer products. This is the outer, these two vectors are being done outer product. So this is a column vector and this is a row vector. So you get matrix for each of the data points and you sum it. So this is a symmetric matrix. Does everyone agree with that? This individual matrix is symmetric. Yes.
Yes.
Okay. Given that this is symmetric matrix, this is also symmetric matrix because sum of symmetric matrices gives us a symmetric matrix. Okay. So yeah, given that symmetric matrix, it will have what are the properties of a symmetric matrix with respect to eigenvalue decomposition? So when you decompose a symmetric matrix, what are the properties? Decomposition using eigenvalues decomposition. Symmetric matrix will have real eigenvalue and orthonormal
Mm.
eigenvectors.
Mm.
Everyone agrees with this? This result is coming from linear algebra. Yeah, is this fine? This specific result So symmetric matrices have real eigenvalue and orthogonal eigenvectors. And what is this? E1 to En. They are the eigenvectors of the covariance matrix. They are already orthonormal. And if you consider all of these orthonormal eigenvalues, I mean they will have n of these orthonormal eigenvectors. So this will give you an n cross n matrix. So it's an n cross n. A is an n cross n matrix which is orthonormal, which is by definition is a rotation matrix, right? Everyone remembers the definition of orthonormal vectors. Orthonormal means what? Ei transpose Ei will be,
1,
and Ei transpose Ej for I not equals to j is
0.
0. So yeah, given that these results are coming from linear algebra, we can easily say that this matrix A is a rotation matrix. So what this KL transform will do is it will then rotate this whole line to this x-axis. That's it. So it will just rotate the whole this yellow line to this x-axis, and yeah, we are done with it. That's what the KL transform does. So here, once you transform this specific line using KL transform, your y coordinate will be 0. If you use uh, all the uh, eigenvectors out there, so your y coordinate will be 0 and the x coordinate will be given by whatever specific transform you see. Is this intuition clear? So now you have reduced the full problem to one dimension. Now you can do whatever you want with your set of data points. Since it's a line, then you can easily say that you just need that line in one dimension. So it's easy to analyze now instead of doing it in two dimensions. Okay, so given this basic line fitting example, we'll now move to the specific question. So here we have the KL, we need the KL transform of the matrix. So we are given these black dots, which are our data points. Our data points lie in two dimensions. I hope it is very clear from the figure because it's an image. And so yeah, your x-axis will vary from 0, 1 like this, and your y-axis varies like this. So what are the set of points that we have given this image? So set of points given are what?
1, 1.
Is it 1, 1? 0, 1. Yeah, 1, 1, 1, 2.
1, 1, 1, 2.
1, 1, 1, 2. Next is what? This is
2, 3. I say 2, 3.
2, 3 and 3, 2. Okay.
4, 3, 4, 4.
This is 4, 3 and 4, 4. That's it, right? 4, 4. Okay. So now, given the specific algorithm, we'll blindly do it. What do we need to do? First, we'll get the mean vector. Mean vector is what we'll just sum all of these divided by the number of elements, the number of points given, which is 1 by 6 times 8, 14, 2, 3, 3, 2. Sorry. Yeah, so this will be 15. What about the below one? 7, 9, 12, 15. So it's also 15. Comes out to be 2.5. Everyone agrees? So this is capital X, which contains these small xi's. These are all xi's. And next step is what? We'll have to reduce the mean. So once you reduce the mean, how does this capital X minus mu look? This is minus 1.5, minus 1.5. Just let me know if there are any corrections required. I think this is fine. Given this, what is the next step? You need to get the eigenvalues. First, you need to get the covariance matrix. Okay. So covariance of X, which is 1 by n summation over I minus mu transpose, and these values are xi minus mu already, and n is 6. So what is it that we need to do? We'll sum this, but I guess I can just copy the specific values with this question quickly. Okay, so let me call this as some zi. So it is 1 by n summation over I zi transpose. Okay, given that this is zi, how will the overall matrix look? 1 by n is 1 by 6, which is kept out. Each of this will be, this is zi1 square. This is what? zi1, zi2. This is summation over I zi2, zi1, summation over I zi2 squared. Everyone is fine with this? So you can write zi as zi1, zi2. Given this, zi transpose will look like this, right? zi1 square, zi1, zi2, zi2, zi1, and zi2 squared. So given this, we are just summing up such matrices 6 times. So we can just take the summation inside and it will look like this, right? Given this specific thing, we have the specific values. You can just compute it later. It is 1.583.916. So as I said, it should be a symmetric matrix. You can clearly see that this and this value are same. So covariance is a symmetric matrix. Now what do we need to do? How will you compute the eigenvalues? Eigenvalues? Anyone?
That matrix minus lambda.
Subtract lambda from the
Yeah. So
1.53.
yeah, subtract lambda from the identity and the determinant should be 0, which
Yes.
physically means that this specific matrix is singular. It is not full rank. And given this, you can solve how many eigenvalues will you have? It's a 2 cross 2 matrix. You will have 2 eigenvalues. You can solve for the specific values. I'm just writing it out. And if we solve for these 2 eigenvalues, how will we get the eigenvectors?
Solve for the null space of C minus lambda. C minus lambda 1 eigen.
Yeah. So if someone says me this is Cx equals to lambda x, or someone says me that this is C minus lambda I times x equals to 0, which is the null space, what should I do? I'll just place the values here, that's it. If I write it in generic sense, this C minus lambda is what? 1.583 minus lambda 0.916 6. This is 0.916 minus lambda. And this is what? It will be some x1 and x2. Okay, people confused. I'm using x everywhere. Maybe we'll write it as v. So this is v1 and v2. Given that this should be 0, since it is in a null space, you can just get these equations. 1.583 minus lambda into v1 plus 0.916 times v2 equals 0. So now you can write it as v1 equals to minus of 0.916 upon 1.583 minus lambda times v2. So when you want to get the corresponding eigenvector for lambda 1, just place lambda 1 here. You have the relation between v1 and v2. Just fix one of them. If you fix v2 as 1, you will get the corresponding v1. And again, do the same for lambda 2. Is it fine? Given this, you will get the eigenvectors. And once you get the eigenvectors, what is it that you need to do? So
Arrange them in
yeah,
lattice.
yeah. So is like your E1 transpose and E2 transpose, where E1 is V11, V12, E2 is V21, V22. Okay. Just arrange them and then that's the whole. Yeah. And then just apply it on these data points. These are the data points that you have with the specific formula. You have mean removed. So we have the mean removed points out here. Just apply A times, multiply the matrix A to each of these points, and whatever the points you get is the final answer. Okay. So these are the transform matrix. If someone asks you for transform matrix, you have to get this matrix. Else, if someone asks you to find the transform of the set of points, you have to multiply this with all the data points. Okay. So given this, we'll move on to the next one. So the Fourier transform of two-dimensional characteristics function is this. Okay. So this is a two-dimensional function which varies with x and y. You need to find the Fourier transform of this. How to do it? How will the function look like? Anyone?
Square.
Okay. So within x, 2 and minus 2, this means x is between 2 and minus 2. This means y is between minus 2 and 2. You have values 2. The intersection of these two areas. This is y2 probably. This is y minus 2. And this is x minus 2. This is plus 2. Given this, our final area, which is between this thing, is, yeah, someone said it's square, it should be square. Okay, so this yellow part denotes the the whole other space is 0, as it says. So how do you get the Fourier transform? What is the formula for Fourier transform? What kind of function is this? Is it discrete or continuous?
Continuous.
Yeah, it is continuous. So what kind of Fourier transform will you apply?
Continuous.
Yeah, so it is the usual. You can call it as continuous time Fourier transform, but people just say it as Fourier transform. So it is not same as DFT. This is discrete Fourier transform. Just be sure about this. Here everything is continuous. Frequency and time both are continuous. And here frequency and time both are discrete. It is not same. Many people do this mistake. This is fine. So let's write the formula. What is the Fourier transform formula? Maybe I'll write it as g of u comma v is equals to Fourier transform of xy. What is the general formula? Fourier transform, continuous time Fourier transform.
Infinity to infinity.
Sorry, your voice is not audible. Can you speak louder?
Is that minus infinity to infinity f of x y e power minus
E power minus
j x u plus y v du dv.
k twice by ux plus vy
Vy
and integration over what?
minus infinity to infinity
Now, they are the limits, but integration over what?
du and dv.
Right? This is forward Fourier transform, right? You have to integrate over which variable?
X and Y.
X and
X
y.
and
Yeah, so there should be two integrations here and then you can write dx here. Is this clear? The forward Fourier transforms map everything from space domain to the frequency domain. So the final answer should be independent of the space variables x and y, but should be dependent on the variables, frequency variables u and v. That's why you integrate over dx and dy. It's a simple way to remember that. Okay. So given this, what is that we need to do? We need to find Fourier transform. Okay. So this signal exists between in the specific square box, else it is zero. So if someone says me that, so I'll just write it is minus 2 to 2, minus 2 to 2 within the value of the signal is 2, okay, into e to the power minus j twice by ux into e power minus j twice by vy dx dy. Is this fine till now with everyone? So I'll just do a change of variable here. I'll write omega as twice by u and sigma as twice by v. Should not matter, right? I'm just doing a change of variable for the independent variables and not on the variables which are the integrable variables. So I can write it as g of omega comma sigma as 2 times integration minus 2 to 2 e power minus j omega x dx. This is again the same case with respect to y. Is this clear? Can we separate this out?
Yes.
Why?
Separability property.
No, separability properties say about what? It states about this. This is the separability property. This is the separability. No one said that you can break the integration like this, right? At least not in the class, but I'm writing it here. What's the point then? Can we do it or not?
Yes, we can do x and y
Yes,
are
we can.
independent.
yes.
It belongs
Yes,
to
but
x
why?
and belongs to that is for x and
Sorry?
it is independent.
Yeah, I mean, okay, first thing is, yeah, these terms are independent of the other variables. The first thing, individual terms are independent. What else? This is, of course, one of the first criteria you would like to use to separate this. And then next, the next is a mathematical aspect to it, that this inner, what do you say? Inner integration is actually gives you some value. It's not going to infinity. Inner integration is finite. So if you do both sides, either do dx dy or dy dx, both are finite, and this and some, so that's the reason you can easily separate them out like this. If the integration is not finite, you cannot do this thing. So yeah, people generally take this thing seriously when you go to a maths professor. Okay, so given this, what is the answer? If minus j omega x upon what? Minus j omega is between minus 2 to 2. This is again sigma y varies between minus 2 to 2. So this part is fine, right? So how do we write it? It's minus j sigma. Given this, what I'll just place the values, e power minus j2 omega minus e power j2 omega is upon j omega. These minus can cancel out. This is j square, which is what? Minus 1. So it is like 2 upon, what is this? Omega sigma. This is what? I can just change the sign here. I just multiplied both of them by minus 1. Okay, so j square is minus 1. This is for j square, and I'll just change the signs for both the cases, so it still remains the same. Now what? This is what? Can anyone tell me what is this? If I divide this by 2, and again I divide this by 2, what is this? This is
J sine 2 omega.
sine 2 omega. This is sine 2 sigma, right? Yes. Or is it j sine 2 omega? Okay, so it is j sine 2 omega. I'll just keep j's here. So given this, we'll have this sine 2 omega sine 2 sigma. So this is 8 upon omega sigma sine 2 omega sine 2 sigma. So this is the final answer. Any doubts? So cos thing will be what? E power j theta minus e power minus j theta upon 2. But then sine of theta is e power j theta minus e power minus j theta upon 2j. Yes, everyone agrees. This comes from the complex numbers. Yes, any doubts? So this is Fourier transform question. And we'll move on to the next one. No doubts, right? Okay, so this is our next question. What is discrete cosine transform? First question. What is DCT? And anyone tell me the formula? That's a big formula. So I'm writing 1D DCT actually. This is alpha k summation of n equals to 0 to n minus 1 xn. Then is it fine? Anything wrong in this?
It's 2n plus 1. Right?
2n plus 1, yeah. Sorry. Okay. So where alpha k is what? 1 by root 10, k equals to 0, or else it is square root of 2 by n, k equals to 1 to. So given that there are n discrete points in your signal, you have the specific DCT formula. Okay, so okay, fine. So we'll move the questions one by one. So is this correct? X of k plus 2n is minus of xk. So of k plus 2n, what is this? Alpha of k plus 2n, summation of n equals to 0 to n minus 1 xn cos of pi k upon 2n. Here we have to add plus pi of k plus 2n plus 1, right? Is this fine? Okay. So we have to see whether it is equal to minus of xk. So we'll first look at this cos term. Cos of pi by 2n, k plus 2n plus 1. How can you rewrite it? Cos of pi by 2n, k 2n plus 1 plus pi by pi into 2n plus 1. Correct? Yes. So what is the specific quantity? This will always be odd, right? Yes.
Yes.
So it's an odd multiple of pi, odd pi into odd. So when you have this cos of x 2n plus 1 pi, or rather, yeah, 2n plus 1 into pi plus some other quantity, what does it give you? How can you simplify this expression? How does cos look like? Where this is what? Pi by 2 and 3 pi by 2. and this is, so you only have this pi here, or multiple of pi, right? Pi, then 3 pi. So what does this simplify to? Anyone?
Minus cos theta.
Pi minus?
You can, I just did cos A cos B minus sin A sin B. So cos of odd multiple of pi is -1.
What about sine?
That's 0, right?
Okay. So you can write it as cos of pi by 2 and 1, cos of this, which is always -1, minus sine of pi by 2 and k of 2n plus 1, which is fine, but sine of this is 0. This part is 0, and this part is -1. So effectively, this thing turns out to be minus of cos pi by 2 and k of 2n plus 1. Okay. So this part is resolved, which is equal to minus of minus of this part. What about alpha? Anyone? So alpha of k plus 2n is equals to alpha k. So given that you have this, it is this specific part is right. Okay. Any doubts? And we'll move on to the next part. C equals to C transport. What is C here? Can anyone say that? C here is the transformation matrix, which is so if you have capital X in the transform domain and small x in the original domain, this is transformed domain. X is an original domain, or the original time domain. So this is the specific matrix that you would have seen by construct using the basis vectors. These basis functions are, I will not say vectors. These basis functions, you can use it to create the specific matrix. So is C equals to C transpose? Hmm? What will be the C be? So here the input variables, this is the variable in small n. So here you have x of 1, x of 2, and x of n. And what are the output variables? Here you have capital X of 1, which is xk. This is xn, this is x of capital N. Okay. So given this, how would the C matrix look like using this formula? Cos of pi by 2n k plus 2n into 2n plus 1. Oh, not this one. Ah, yeah, this pi k upon 2 n into 2n plus 1. So you have to take it from n equals to 0 to n minus 1 and not. How do you do it? 1 to x0 to xn minus 1. This is in the transform domain. K is some matrix times x0 to x of n minus 1, right? And this is the matrix C. This is in the time domain n. Given this, how will the matrix look like? Just place the value C. Value for 0 comma 0 will be what? K is 0, n is 0, which is cos of pi by 2n. Cos of pi by 2n. Next is, and alpha is 1 by root n. So 1 by square root of n cos of pi by 2n. What is next? 0 comma 1. That means n is 1, small n is 1. Cos of 3 pi k upon 2n. This is by square root of 2 by n cos of 3 pi k 0, right? Sorry. If k is 0, you have to put it 0. Cos 0 is 1. All of this will turn out to be 1 into 1. This is for 0 comma 0. Yeah, so the first row will be the same. 1 by square root of n. 1 by square root of n. This is for 0 comma n minus 1. It's also the same. What about the first column? Is it the same? Cos of this is k equals to 0 row. We will write k equals to 1 and we'll get to see. K equals to 1 is what? Cos of pi by 2n, 2n plus 1. N is 0 for the first place. So what I wrote there needs to be written here. Square root of 2 by n cos of pi by 2n 3 pi by 2n. N equals to 0, right? Sorry, cos of pi by 2n. This is square root of cos of pi by 2n. Sorry, square root of 2 by n cos of pi by 3 pi by 2n and so on. Can you see, is it symmetric? Is this matrix C symmetric? That's what is the question, right? Not symmetric.
No.
Yeah. So here value of n is 0, 1, n values like this, k values like this. Okay, so yeah, it is not symmetric. So C is not equals to C transpose. But what about C inverse? Is C inverse equals to C transpose?
Yes,
Yes. Why?
because ortho not orthogonal.
Yeah, this is an orthogonal transform. You can say it as unitary, but yeah, orthogonal is orthonormal is better. Or maybe they are using orthogonal transform, so I'll use the same. Okay. So what about the third part? The basis vectors of the cosine transform are eigenvectors of symmetric diagonal matrix. Yes, no? Anyone? Basis vectors are fixed for cosine transforms, Fourier transform, right? They are not dependent on any other transform, any other thing. They are fixed. So given that there is no symmetric diagonal matrix which exists for this specific case for the cosine transform, so it is wrong. Cosine transform has poor energy compaction for highly uncorrelated data. Is it true or false? What is energy compaction property? Yes, anyone? Energy compaction is most
Energy is conserved,
energy is
but
conserved. Okay, that is
uh, but
partial
it is
spread.
unequally.
Yeah, it is not spread equally. So most of the energy lies in a very few coefficients, few transform coefficients. Well, here the transform is dct. So dct has this energy compaction property, so it cannot be poor. It is false. Okay. What about dft? Does it have energy compaction property?
No.
No. Are you sure? If you have seen the examples in the class, those figures of the log of the magnitude of Fourier transform, how do they look? So most of the energy is still concentrated in some areas. But for discrete cosine transform, the area is even smaller. Of course, it also has energy compaction property, but the point is it's not as good as DCT. I'm talking about DFT. So DFT is okay. You have some energy compaction, but DCT is the good one. Okay.
Okay.
Any doubts in this question? I think did we cover all? Okay. Yeah. Any doubts in this question? We move on to the next one then. So we need to find the orthogonal basis. Okay. Find the orthogonal matrix. So this is with respect to the KL transform, and we are given a matrix A and an image, transformed image V. We should find the original U. So whatever we did earlier, this KL transform, what was assumed here? This is a vector, right? This thing is a vector, and our output is also a vector. Yes. But what we have now, each of these is a matrix. Yes. Agreed.
Yes.
Yeah. So what? Why do we have a matrix? Because we are given an image. That's why we are having a matrix. So if I just write that vector minus mu, yeah, this is when x, mu, and y are vectors. But we are given here that x is a matrix. So I'll write capital X is a matrix in this case. So what is the KL transform? KL Yeah. What is the KL transform for matrix? So what would be the equivalent V here? It's given as V in this question. So V will be related to the original matrix X, or I will just use the same notations. U as what? Hmm? What is okay? What does this do? What does this matrix A do? It takes each element of X comma mu and then maps it into Y. This is also a vector, right? So what is it effectively doing? It is taking each row. So if this is an n cross 1 matrix, it is taking each row of it and then mapping it to, I mean, if A is full, if A is an n cross n matrix, then it is mapping it to a n cross 1 matrix. It's now I'm just talking it in terms of matrix, right? It takes an n cross 1 matrix and transforms it to another n cross 1 matrix. But since we have a matrix U here, what is to be done? You will of course transform the rows, but you have to transform the columns, right? This transforms the rows, but you also have to transform the columns when when U is the input matrix. Yes,
Yes.
agreed. So how will you do it? Left multiplication transforms rows. What multiplication will transform columns?
8 multiplied by 8 transpose,
Why A transpose?
transforming into columns.
Mhm. Why not A?
No, A transpose, which will transform into
Yeah, at
rows and
the
columns.
yeah, for the right multiplication,
Yeah.
why do you want to use A transpose instead of A? Okay, so to put it this way, our input data, uh, each dimension of input data, rather A maps from input domain D to output domain D prime. Okay, but what does A? So what is the uh, right multiplier of A? It should be in the domain D. Whatever is the output, it should be in the domain D prime. So when you have to multiply with a matrix, your input domain should also be D, which you can only guarantee if you want to right multiply with A transpose, right? This this is D prime and this is D. So now to make this one D, you have to do a D. You have to take a transpose, and whatever output you get will be D prime. Agreed? So the input domain should be the same. So U is the same input domain, but since you have taken columns, you have to multiply it by A transpose. So your effective transformation looks like this: U equals to A U A transpose. And what are you given in the question? Sorry, V equals to A U A transpose. What are you given in the question is V and A. So what is the relation between U and V now? I can write U as what? Okay, I will go stepwise. V equals to A U A transpose, which implies A transpose V equals to A transpose A into U A transpose. This is what A transpose A. One more step then. A transpose V I'll write multiplied by A. A transpose A U A transpose A. What is this? A transpose A is what? Identity, right?
Identity. Huh?
Why?
Huh.
Why is A transpose A identity? A is orthonormal or rotation. Yes. So what does it lead to? U is A transpose VA. Now you are given V and A. You have to just find U. I think this is just matrix multiplication. And just place the values and you can get it. So it is 1 by root 2 times. If you see, is A orthogonal in the given question? Yes, no? Column multiplied with itself is? Dot product of column with itself is? By root 2 this into this 2 by 2, right?
2
Dot
by
product
2.
is 2,
Yes.
is
Minus
1. And
1.
what about the other column? Dot product is 0.
0.
Yeah. So it is orthogonal, orthonormal matrix. So it satisfies the constraint for being the transform matrix or KL transform. Okay. So it is 1 by root 2 times 1, 1, 1 minus 1. B is 4 double again 1 by root 2 times 1, 1, 1 minus 1. Given this, we have what? Half this first. Copy the first row. And this is what? Yeah. So your original image is this. Note that this is equal. This is original image, but me with mean shifted. It is not
Yes.
the exact original. Original image shifted mean. Zero mean. I will not say zero mean because we are not given mean, so we cannot exactly recover the original image. That's all we can recover. Okay. Any doubts? Okay. We'll move on to the question. So since we read about discrete wavelet transforms as well, We'll have to see what DWT means to us. Okay, so we are given data points like this. Not data points, it's a signal. It varies with time like this 3, 4, 3 minus 2. Okay, so what is the DWT of this specific signal? How to do it? Okay, first of all, what is Haar transform? What are the Haar wavelets? Anyone? Haar wavelets? How do they look? The Haar is the simplest one actually. So this is still where the signal exists. Yeah, so this is the point where the signal exists, and this is Haar wavelets, different Haar wavelets that I'll be drawing on this axis. How many Haar wavelets will you need? What is the size of the input data? Input, input size is 4, right? Size is 4 in the sense it's yeah, only for 4 time instances it exists, otherwise it is 0. So the Haar wavelets look like this. If I call it as maybe W1, it varies with respect to time like this. All these are time axes. So maybe this is 4, since this is the end, this is 0. How should it look like? So the first one is constant, which is half. The second one is what? Second one should lie, should change at the middle, which is first it's half, the rest it's minus half. Third one is what? What should it be? See? Okay, third, should the third one be? What are the two things that you can vary in wavelets?
Time of
Sorry,
is the
can you
time
speak
of
loudly?
frequency?
Huh?
Frequency?
Yeah, A and B, which is the scale, and
Frequency?
frequency is scale, and the other one is
Time. Uh,
yeah,
time.
time shift is translation. That is what the terminology being used in the lectures. Okay, so you have this. So here you are changing the scale, right? Changing the scale. So first the scale is like this. You reduced it to half. It becomes like this. Now you reduce it to half further. It will look like this. And this is minus half. What about the fourth one? So here it will go to 0, by the way. Here it will go to 0. And so we are only varying scale here. What about translation? So we are unable to capture this part. So we'll now translate this specific wavelet here. So our wavelet will start like this, go like this, and then go 0. So this is again half, and this is fine. So these are the two things that we varied. Most the first three we just varied the scale and we got it. But since this is not being captured, this part is not being captured with this specific wavelet, we will have to translate it so that we are able to capture this. So given this, how do you write the Haar transformation matrix? So what will be the transformation matrix? Since we have four data, uh, 4 points which has data, x0 is okay 3, 4, 3 minus 2. This is 3, 4, 3 and minus 2, right? Given this, what is uh, we'll have to encode this into a matrix. Once we encode this, whatever output we get is our answer. This will be the discrete wavelet transform using Haar wavelets. Okay, so what is this? How will you encode this? What does this mean? How does your signal look like? It will be somewhere 3, 4, 3, 4, 3, and then minus 2. This is your signal x of n with respect to n. So you need to take the discretized version, the discrete version. So instead of t, you take n, and it only exists at discrete points, not everywhere. That means it will exist here, 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 and here, for instance, the middle point. Okay, given this, how will you now write the transformation matrix? So what does wavelet transform do? You multiply the corresponding elements, right? That's all it does, right? So when you multiply the corresponding elements, how will it look like? So it is 3, 4, 3 minus 2, multiplying it with half everywhere. So your first wavelet, this is your first wavelet. Fine, all of these are halves. The next wavelet, how will you represent it? First two is half, the rest two are minus half. Yes, is it fine? The third wavelet will look like this, which is half half, and then the other values are 0. So maybe I'll just put a dot here to make it clear. So these are 0 values, and the fourth wavelet is it will start with zeros but end with half and minus half. Fine. So what does this do? We'll just plus 3,
So
7.
one doubt,
Yeah.
sir. You are giving these values. That is this this wavelet you are drawing by yourself or some maths for that. That is this half these waves you are drawing simply or
No, no. So this is the standard Haar wavelets. That's how it is defined.
okay, fine. Thank you.
So yeah, the three properties that we discussed about wavelets is yeah. So the frequency should vary, right? So here the frequency is varying. That's varying in terms of scale. The second property is it exists for limited duration. That means after a specific time t, which is 4, it does not exist. And also in the specific case, it exists only for a smaller amount of time than the whole time t. And the average value is 0. Here if we extend this wavelet, the average value will be 0. But here in these cases, you can clearly see that if you sum all these values, it will be 0, right?
Okay, okay, sir.
Yeah. So it satisfies all the three properties that we discussed, and given this, we can just write the answer right here. This is 4, 3, half, and 5 by 2, 5 by root. 5 bit. Fine. Yeah. Okay. So is this fine?
Yes.
So this would be our last question for the day. Each one of the following vectors cannot represent principal component. So this is three vectors. I have one more out there. And this is the fourth vector. Okay, so what is the property that these vectors should satisfy for it being a principal component? Principal components are principal components are what? Ortho,
Orthogonal.
normal, right? Given this, we'll try out the first one. So let us call these first vectors as v1, second vectors as v2, and third vectors as v3. So I'll write the option numbers here. The first one is what? So v1 dot product with v2 is what? 0. Okay. v2 dot product with v3 is also, this is what? 1 into 1 plus 1 into 1, 2 minus 2, 0. So if these two conditions satisfy, is the third condition automatically satisfied?
Yes.
No, we are
Hmm.
in 3D space, right? So if
Yes.
I give you x and y axis, they are
Yeah.
orthogonal. If the third one is also x axis, then you can do these two things, but this will not be 0. So you have to check for all three possibilities. So since these are zeros, and what else? Orthonormal means v1 transpose. Okay, so these are not really orthonormal vectors. I would just keep it as orthogonal. But yeah, when you take the eigenvectors, then they should be orthonormal. But these do give orthonormal vectors if you just divide it by the norm. Okay. What about second one? V1 transpose V2 is minus 2, right? Second one is not, cannot represent the principal component. What about third one? Oh, third is same as the first one. Fine. What about the fourth one? Fourth one has again the same problem, although it is not the same. Yeah. So again, third is same as first. And for the fourth one, you can see that V1 transpose V2 again is minus 2. So yeah, here the last element here is different. Fine, but since any one of them is not satisfied, you can say that they cannot represent principal components. So yeah, these two can represent, these two cannot represent. These two can. Okay. Okay. I think
Yes.
yeah. Any doubts? Okay, then I guess we can end the session here. If you have any doubts, you can ask me now. I'll We'll meet next week same time.
Lalit, I have one small question.
Yes,
I'm getting a different question set. So is that with everybody or
different question set for what?
these assignments? I'm getting different question. Other
Dif-
than these questions, there are different questions.
In the sense that, okay, whatever I'm solving is
This question was not there in my assignment.
that's okay. I'm not specifically solving this year's assignment.
Okay. So
So these are,
that's what I just wanted to
yeah. So
confirm.
these are from previous year's assignment, but
Fine. Yeah.
some of the questions can match. Probably should not
Yes.
match, but not all of them will match.
That's okay. Yeah. Thank you.
Yeah. Okay then. See you guys next week. Thanks for joining.
Thank you. Bye.